Okay, so random forest. I don't know what time is it. It's half. Okay, 20 past 9. We will do some breaks, okay? Don't worry. So random forest. Okay, this method is actually derived from another classification method. I don't know if you know it. Is it called classification trees? Okay. Have you ever heard about classification trees? No. Okay. So we are going to see what is a classification tree, and then we will see what is it a random forest. Because as the name says, okay, a random forest is a forest made by several trees. Okay. So the idea of random forest is to have different models. Okay. It's a kind of democracy, okay, in machine learning. So you have several models, okay, and you use all these models and you do an average, okay, to get your prediction. It's what we do in democracy when we vote, okay? A lot of people vote and then we do a kind of average, okay, to decide more or less, okay? It's the same, okay? So, but as I said you, okay, a random forest is made by several individual classification trees, okay, as in a normal forest we have, okay. So, what is it, a classification tree? Okay, a classification tree is a very simple way to do classification, okay. So, what does it mean, classification? Just to have a, you know, a bit of introduction, a short abstract. I mean, classification is a supervised approach, is a model, okay, to predict a qualitative class for your data, okay? So, let's do. Usually, you have your data set, okay? I don't know on which kind of data you work, but let's say yesterday I saw a lot of spectroscopic stuff, okay? So your data could be samples on the rows, and then the signal you measure, okay, on different wavelengths, okay? And these are the variables, okay? These are your independent variables, and then you have your class, okay? A class is a label, okay? It's a qualitative label. So for each sample, for example, you know that that sample is in a positive or negative class, for example, okay? You can have two classes, you can have more classes, of course, okay? I don't know if you work on food typicity, for example, your class can be the geographical origin of a food product, for example, okay? Then, with this data you can build your classification model, then you get a new sample, you measure your variables, but you don't know, okay, this is a question mark, okay? You don't know the class, okay? And you can use the classification model to predict the class. Okay, so the classification model will predict this sample as positive or negative. There are many ways to classify. Okay, there are many algorithms. Okay, one of these is the classification tree, which is one of the most, I think, simple.
You have all the stuff here.
Okay. Which is one of the most simple way, okay, to do that. How does it work? It's more difficult to explain than looking at it with an example, and we will do that, okay? But just to start, you have your full set of samples, okay? And then you try to separate the classes. Let's say just to simplify, we have just two classes, okay? We have positive and negative samples. So you try to separate these classes by using a split, okay, of your data. So on each split, okay, you separate the samples in two subsets. Okay, so let's say we have the full set of our training samples, and then we separate this at the first split. Okay, we separate these samples in two subsets. Okay, like here, and then we go on. Okay, and we define a lot of subsets of samples, but we try to have in these subsets only samples belonging to the positive or the negative class. Okay? This is the way classification trees work. So how does it work? On each split, okay, which is called a node of your classification tree, we, or better the algorithm, find a variable, one of the variables we have, okay? So it selects one variable, which is the best variable in that moment for that set of samples to separate the classes, okay? Separating the classes means that what you do, you reduce the entropy, okay? So you maximize the purity of the classes in these subsets, okay? And this node, okay, with this node, then we have a rule to define the two subsets of our samples, okay? Let's do an example. I need some colors. Let's say we have measured, I will use stupid examples, okay, but just to understand, okay? Let's say we have two variables, okay? These are the variables we have measured on a set of samples. And we have these samples and we have three classes, okay? Let's say these are two chemical variables you measure on, I don't know, wines, okay? And the red class are Spanish wines, okay? The blue class are French wines, and the black class are Italian wines, okay? And I want to build now a model to classify these three classes on the basis of these two variables, okay? In real life, this will never happen, okay? Two variables are not enough, but it's just to understand. So, if you look at this plot, I mean, it's easy to find boundaries, okay, between the classes. Okay, how does it work with classification trees? So, we start with all our data set, okay, and then we have to define the first split, so the first node, okay. So, we have to find the variable, okay, one variable, which is able to separate these samples in two sets, okay? And these two sets have to have the maximum purity. So it means that in these two sets you have to have the highest, the maximum purity of one of the classes, okay? In your opinion, which is between these two variables, the variable which can split better the three classes, just one of the two? Variable number one, right? Okay. And the split would be here, right? Okay. So, to clean. Okay. let's put because I need it, also a quantitative scale of this variable and another quantitative scale of this variable, okay? So let's say this variable ranges from 0 to 10 and this from 2 to 100, okay? So the best split between the three classes, the first one is this, okay? On this variable, and let's say we also have to define a threshold, okay? And this threshold is 5, okay? So the first node is with variable 1, and the first threshold is 5, okay? This is the first split we do, okay? Then all samples which have a lower values for the first variable than the threshold goes to the left. We split in two subsets, okay? The others goes to the right, okay? So on the right what we have? All the samples belonging to France, right? And this is a pure subset, right? Because we have only samples, only blue samples, okay? So we have finished it here because we have been able to separate one class, okay? Then here we have in this subset we have all these samples, right? Now we have this subset. We have two variables, which is the best variable to separate all the samples which are in this subset. Variable number 2, and which is the threshold 50, okay? So we put here variable number 2, the threshold is 50, I can write it, right? Okay, this is 50, okay? And we split again the data, okay, in two subsets. If the variable number 2 is less than 50, okay, then you have the pure black class, right? Which is the Italian. Otherwise, you have the pure red class, right? Which is the Spanish one. Okay? Yeah? If you reverse this plot, it looks like a tree. Okay? This is why it's called classification tree. And this is your model. No coefficients, no inversion of matrices, whatever. Okay, it's very simple. Now, you get a new sample. Okay, so you measure a new sample, and you don't know if this sample belongs to the Italian, Spanish, or French class. Let's say your sample is here. Okay, you measure variable 1 and variable number 2. Okay? Now, it enters here in the classification tree, and we have to apply these rules. For this new sample, variable number 1 is less or higher than 5. Higher is French. Easy. Okay? Even my daughters, they are 8 and 11 years old, can use it. Okay? You don't need math. Actually, you don't need MATLAB. You just need a piece of paper. Okay? This is the idea. Here is easy, okay? But the idea is to find at each node the variable which maximizes the purity of the classes. Okay? And also a threshold, okay, to define this split. Yeah.
But then the nodes are ranked by importance, right?
Yeah, because you, in this way, somehow, you do variable selection. You know what is variable selection? You maybe have 100 variables, but not all the variables may enter this tree. Maybe there are only 5 or 10 of the 100 variables. Okay, so only the important variables enter the tree. Okay. Of course, I would expect in the first nodes to have the most important variables for discrimination. Yeah. Yeah.
And can you reuse variables that you have used before?
Yeah.
So it might happen that variable 1 separates between two classes and
Then
again,
you have
again variable
number
1 in
2
another.
and then again variable number 1. We will see it. Okay. Yeah. Okay, but the idea is very simple. Another very stupid example. Okay, we want to discriminate male and females. We just use two variables, age and weight. Okay, this will never work, but just to give you an idea. Okay, so first variable most important for the splitting is the age. Okay, the threshold is 180. So if a sample has age lower than 180, okay, it goes this way. Otherwise, this way, and it is classified as male. And then here you have another node, okay? And these are the terminal nodes where you have the classification, okay? Yeah.
There is a question. Often when data variables are at least partly correlated, meaning that when the data that you represented probably are rotated, at least.
Yeah.
How do you do in that case? Because in this way, in the way that you presented, the separation is let's say values that are, let's say, perpendicular to the.
Of course, usually classification trees are more complicated than these ones. So you have you need more nodes to explore better and to separate better the classes. Okay.
Yeah.
But the classification trees by itself is very simple, but it has some bias. Okay, because it cannot. The idea of random forest is to use several classification trees. So classification trees by itself is thought as a weak classifier, not a very good classifier. But the idea is to put a lot of trees together and to do a forest. Okay. Yeah. So, okay, this is what we said before. Okay. So, for each node, you look at the best variable. Okay. Giving the purest subsets. Okay. So the subset where you have best ratio of samples. Of the partition of samples, okay? And for each variable, then you have to define a threshold, okay? And then you have a rule, okay, associated to each node to split your data, okay? This stuff, just to give you a technical detail, so how do CART select the variable which gives the purest subsets? Okay, it can do in different ways. Then there are, of course, different versions of classification trees. But usually, algorithms use this index, which is called the Gini diversity index. Okay, so it looks for the variable which minimize this index. Okay, where you have somehow represented the entropy. Okay, so the diversity you have in the samples you have in a subset. Okay, this is the total number of samples. This is the number of samples you have in one class. Okay, so if in a set you have just samples of one class, okay, this is minimum. Okay, and what cards use to select each node is this index. Okay, so for all the variables, it calculates this index and then it selects the variables which minimize this stuff. Okay, what was that?
I'm thinking.
Okay. Okay. And that's all. Okay. So this is another, for example, another example. Okay, very similar to what we have seen here. Okay, even here you have a clear linear separation. Okay, so how CART would handle this data set, of course it would look at, okay, even here, I mean, stupid example with just two variables, okay, you have the red and the black class. So, first, it looks at which is the variable giving, again, the best split, okay, and which with the which threshold, okay. And it would find the best variable is variable number 1, and the threshold is this one, okay. Then, if a sample has a value of variable number 1 higher than this threshold, then it is red, otherwise it's in this subset. Step further, then, okay, it has to separate this subset of samples, okay, and of course the best variable is variable number 2, and this is the threshold, okay. So, on this subset, if a sample has a value lower than this threshold, then it's red, otherwise it's black, okay. And even here we have a simple classification tree, okay, with just 2 nodes. But of course, I mean, you can, yeah.
Can you go back?
Yeah.
So then how do you prioritize the classes? Because in the first separation, x1, if you establish a threshold in 0.4, that one, instead of 61 is 0.4.
It depends on,
This
is just visual example.
Okay, okay.
Okay, but it's, we should have a look to the...
But you know what I mean, right? I mean, if we put the threshold at 0.4,
yeah,
you will
can
separate the
separate
red.
Yeah, and
But
then,
you are
yeah, but
including
then
black
probably...
dots.
What?
But if you do that, you are including also black dots.
Like in the other one.
But
In
probably
06
if
you also
put a-
include black
if you put a
dots
split
and red
here,
dots.
then it's not easy to separate. I mean, then the remaining,
Yeah.
the remaining is this one, okay?
Yeah.
I mean, you have the pure black class,
Mm-hmm.
but then you have this subset, and you cannot separate these 3 samples, for example.
Mm-hmm.
It's, I mean, it gets more complicated,
Yeah.
okay?
Yeah. But how does he know that it's x1 and that's threshold?
Because with this stuff, okay, it looks at which is the purest subsets, okay,
Mhm.
and it use it, okay.
But it's the same, no? When you say if it is lower than 0.4, then everything is black. So it's the same, but
But it depends on the ratio you have. Anyway, I mean, this is just a visual example, okay? So don't just look at how, I mean, just understand how does it work here, okay? Wait, I want to show you something, but where is it? Okay. Do you know the IRIS data set? Very simple data set with 4 variables, okay? 3 classes and 150 samples, one of the classical data set in machine learning. This is the classification tree, okay, for that data set. Okay, so there are 4 variables, but you can see there are 1, 2, 3, 4 nodes, okay? There are 3 classes, 1, 2, and 3, class 3. These are the splits, okay? And can you see, I mean, we have 4 variables, but in these 3, only variable 3 and 4 are selected, okay? Variable 1 and variable 2, they are not selected. This means that the most important variable, okay, are variable number 3 and number 4, and that you just need these 2 variables. So you do an implicit variable selection, okay?
And the funny thing is that it's only just a threshold, pure threshold.
Yeah.
It's not a conditioning threshold, it's not an interval threshold.
Then people proposed
Ah.
modifications where instead of 1 variable, you, for example, can have a linear combination of
Yes.
variables. You can, you have all the yeah. This is
Fast.
the most simple.
Okay.
This is the most simple approach. Okay. And for example, here also you can understand that variable class number 1 is the most easy to separate. Okay? While to separate class 2 and 3, you need more splits. Okay? In a recursive way. Yeah. Let's go back. Here, just to let you know, okay, when you have these are very simple data set, but if you have a lot of samples and a big overlap between the classes, then the tree can be really more complicated, okay? Let me see if I have, I don't know. Maybe on MATLAB later we can see one example. So another thing people do is the following. Let's say we have a very complicated data set. Okay? With a lot of variables, a lot of classes. Okay, let's imagine you have, instead of 2 or 3 classes, you have 5 classes or 10 classes. So you need a lot of splits, okay? So you may have a very complicated tree. Like this one. Okay? This is quite, common when you have not very complex, but not simple data set, let's say, okay? Maybe you have a tree like this. And if you think how CAD works, it's very easy to do overfitting. Because if you have a subset of sample, you can always find, and you have a lot of variables, you can always find a variable to separate these samples, okay? So, maybe let's say in this set, okay, in this terminal node, you have, 2 positive samples and 2 negative samples, okay? Which means you will have some errors here, okay? Because you have like an overlap. But if you have a lot of variables, maybe there are some variables that by chance can separate these two, okay? Maybe there are some variables that can separate 1 positive here, and 1 positive and 2 negative here. And then there is another variable which can separate 1 positive here and 2 negative here. Okay? And then you have like perfect separation. But this is kind of overfitting. So, one thing you can do when you have a tree, what do you do when you have a tree? Usually, you do pruning, okay? So it's the same. So when you have the full tree, then by means of cross-validation methods, you prune it, okay? So you try to simplify it in order to avoid overfitting. And so you try to eliminate this, okay? Of course you accept to have some errors because it's natural to have errors, okay? And you try to maybe have a situation like this one, okay? So pruning is an operation that people usually do when doing this approach, okay? And it is usually based on cross-validation, okay? Is it clear? Yeah? Okay. Classification trees in my idea is a very simple and straightforward approach, okay? But they are somehow like weak classifiers. So the idea of a random forest, okay, is to put together a forest of classification trees. So to use a lot of classification trees and then to somehow average, okay, the predictions of all these trees. Okay? So, how do we put together a lot of trees? in this way. So, do you know what is bootstrap? What does it mean? Yes or no? It's better to repeat. Okay. So what happens? We always have some samples, okay, which are called training samples, okay? Okay, then we have the class, whatever. So when Bootstrap is a, how can I say, a resampling procedure which is used in validation, okay? It means that you select some of the samples of your training set, okay? And you, how can I say, repeat these samples. Okay, so you duplicate these samples in the data set. Okay, let's do an example. Let's say we have 50 samples in our data set. Okay, we take some of these samples and we duplicate them. Okay, and we form a new data set. Okay, made by 50 samples, but some of those samples are duplicated. Okay? This means that some of the original 50 samples are not included in this data set, right? Okay? And we left out these samples. Okay? So this procedure, you usually use this procedure for validation of models, because you left out some samples, okay? And you have a data set which is constituted by the same sites, but some of the samples are repeated randomly, okay? So usually you do this stuff many times, and you repeat the same procedure for many iterations, okay? So you have your data set, and then you have some of these samples are left out, and some are repeated to constitute again a set of 50 with 50 rows, okay? But some are duplicated, okay? And I don't remember why, for a statistical reason, when you do this procedure, okay, the left out samples are more or less the 50% of the original samples. So if we have 50 samples and you do this procedure, more or less you leave out 15 samples every time. Okay? This is Bootstrap. So here the idea is I take my training samples, I do Bootstrap. So I leave out some samples, and I use the remaining ones, okay, to train, to build a classification tree, okay? Then, and this is my first tree, the first tree in my forest. Then I do it again. Now the samples will be different, right? They are not always the same, because I select these randomly. So I do the same, but this, let's say, temporary set, which have been selected by means of Bootstrap, okay, is different, and I use this set to train a new classification tree, which will be similar, but not exactly the same as this one. Okay? And now I have two trees. And I do it again, several times. Okay? And in this way, I have a lot of trees. Okay? Each tree is calculated with a subset of samples selected by means of bootstrap. Okay? And then, of course, I have some samples which are left out. Okay? And in this, let's say, environment, these samples which are left out are called out of bag. Don't ask me why. Okay? So, but if you go to the MATLAB pages for random forest, you will find that terminology, out of bag. Okay? Out of bag means the samples which in every iterations were left out, okay, from this set. Okay? So in this way I calculate several trees. Okay? In the way we have seen before. Okay? So each of these is an individual classification tree, as the one we have seen before. Then my forest is grown. I get a new sample, unknown sample. I don't know to which class this sample belongs to. Okay? And what I do, I use all the trees to predict. Okay, this is the democracy step. Okay? So I use all the trees to predict the unknown sample. Okay, let's say the most easy case, we have two classes, positive and negative. Okay? Simple case, we have just six, we have a small garden, so we have just 6 trees. Okay? The unknown sample is predicted positive by 5 trees and negative by 1 tree. Okay? Then, of course, the probability this sample to be positive is much higher. So I will predict this sample as positive. Okay, that's all. This is the idea. But the idea is that if I put together several weak classifiers, but they say me the same thing, then I would expect this prediction to be correct. Okay? So averaging